The Big Bang is a concept that has shaped our understanding of the universe, laying the foundation for modern cosmology. Based on Einstein's theory and what is recognized as standard cosmology, the Big Bang was the moment when the cosmos began its expansion, marking the creation of all matter, energy, space, and time. This event occurred approximately 13.8 billion years ago and led to the vast universe we observe today. However, recent developments in cosmology suggest that the Big Bang might not be the absolute origin. Instead, there may have been a phase before the Big Bang that was equally influential in shaping the universe as we know it. This earlier period is referred to as cosmic inflation. Inflation is one of the most captivating aspects of contemporary cosmology. It proposes that before the hot, dense state of the Big Bang, the universe underwent a remarkably rapid exponential expansion. During this period, the universe was doubling in size at an astonishing pace. To demonstrate just how extreme this expansion was, if the universe started smaller than an atom, it would have expanded to be far larger than the entire observable universe within a nanosecond, approximately a millionth of a second. This stage of growth didn't last long, but it played a vital role in shaping the cosmos. When inflation concluded, the energy driving this expansion was released into space, warming it up and forming the particles of matter that make up everything we see in the universe. In many ways, inflation is the precursor to what we call the Big Bang. While the theory of inflation is widely accepted in cosmology today, there are still many unresolved questions. For instance, we don't yet understand what triggered inflation in the first place, what caused it to stop, or how long it lasted. These are open questions in cosmology, and solving them is crucial for a deeper understanding of the universe's origins. Before inflation, the universe was an extraordinarily dense, tiny point of matter, often called a singularity. From this singularity, the expansion began and eventually led to the creation of atoms, molecules, stars, and galaxies. The idea of the Big Bang as the beginning of everything is appealing, but modern cosmology points to a more intricate picture. Some theories suggest that the universe underwent a period before the Big Bang. During this time, inflation triggered the universe's expansion exponentially, doubling in size at least 80 times in an instant. This rapid growth was powered by a mysterious form of energy that permeated empty space. When inflation ended, the energy that had driven this expansion was converted into particles, heating the universe and resulting in the hot, dense state we refer to as the Big Bang. This inflationary stage was cold and void, but it laid the groundwork for the creation of the universe and matter that we observe today. One of the more speculative ideas in modern cosmology is the theory of eternal inflation. This hypothesis suggests that inflation didn't stop everywhere at the same time. Instead, it ceased in different regions, creating many separate zones or bubbles, each of which could be a universe in its own right. Our universe would just be one of these patches. According to eternal inflation, there could be an infinite number of these universes, each with its own set of physical laws and constants. This is where the concept of the multiverse enters, the idea that our universe could be one of many, or even an infinite number of universes. If this theory is correct, it might explain why our universe is so finely tuned for life. In this multiverse scenario, every possible combination of physical laws could exist in different universes. We just happen to live in one where the conditions are just right for stars to form and for elements like carbon, oxygen, and others necessary for life to emerge. Although theories like eternal inflation and the multiverse remain speculative, the idea of inflation itself is supported by empirical evidence. The strongest evidence for inflation comes from the cosmic microwave background radiation, CMB, the oldest light in the universe. The CMB was released 380,000 years after the Big Bang, when the universe had cooled enough for atoms to form. At that point, the universe became transparent, and this light has been traveling through space ever since. By studying the CMB, cosmologists can essentially take a baby picture of the universe. The light offers clues about the universe's earliest moments, helping researchers understand what happened just after the Big Bang and providing evidence in favor of the inflationary theory. One of the most significant findings came from the European Space Agency's Planck satellite, which took precise pictures of the CMB. These images show slight variations in the temperature of the early universe, and these variations match the predictions made by inflationary theory. This experimental confirmation strengthens the idea that inflation is not just a speculative theory but a key element in our understanding of the universe's origins. Understanding the Big Bang and what came before it requires combining two of the most significant theories in modern physics: Einstein's theory of general relativity and quantum mechanics. General relativity explains the large-scale structure of the universe, such as the behavior of galaxies, stars, and planets. Quantum theory, on the other hand, explains the behavior of particles on the smallest scales. To answer the ultimate questions in cosmology, such as what space and time are and where the universe came from, scientists need to develop a theory that merges these two frameworks. This would allow us to understand not only the Big Bang but also the conditions that led to it. One of the more surprising characteristics of the universe is its size. The farthest objects we can observe are about 47 billion light-years away, meaning the observable universe is roughly 94 billion light-years across. This may seem paradoxical, given that the universe is only 13.8 billion years old. How can the observable universe be larger than the distance light could travel in the age of the universe? The answer lies in the fact that the universe has been expanding throughout its history. As the universe grows, the distance between objects increases, extending distant objects beyond the time it would take light to reach us. Most scientists believe that the universe extends far beyond what we can observe. In fact, it's possible that the entire universe is infinite. The observable universe is simply the part we can detect, limited by how far light has been able to travel since the Big Bang. It's possible that vast portions of the universe will never be visible to us. While it's plausible that the universe is infinite, the question remains: is there anything beyond the universe? Most scientists don't believe there is a beyond. If the universe is infinite, it would just continue forever. Even if the universe is limited, it might not make sense to talk about anything beyond it. Space and time are properties of the universe as a whole, and the concept of beyond the universe may not have any physical meaning. The start of the universe is a topic of intense study. Additionally, its final outcome is uncertain. The best current estimate is that the universe will continue to expand forever. This is due to a mysterious force called dark energy, which is causing the universe's growth to accelerate. Prior to the discovery of dark energy, scientists believed that the expansion of the universe would eventually slow down due to the gravitational pull of matter. There was even the possibility that the universe could stop growing and start collapsing, leading to a big crunch. However, dark energy seems to be pushing the universe apart more and more quickly. If this acceleration persists, the universe will never stop expanding. Eventually, galaxies will drift so far apart that they become isolated from each other. In this scenario, the universe would become cold, empty, and dark. Stars would die out, and all matter would eventually deteriorate. This fate is sometimes called the Big Freeze or heat death. The story of the universe, from its beginning to its potential end, is one of the most profound and complex narratives in science. While we have gained substantial insights into the universe's beginnings through inflation theory and the study of the cosmic microwave background, many questions remain unanswered. What triggered inflation and what caused it to stop? What lies beyond the observable universe? If there is a multiverse, how many other universes are there? As scientists continue to explore the cosmos with advanced technology and theories that combine quantum mechanics with general relativity, we will undoubtedly learn more about these enigmas. The search to understand the universe is ongoing, and each discovery brings us closer to answering the ultimate questions of existence. Exploring the origins and structure of the universe is not just a scientific endeavor. It also raises philosophical questions about existence, reality, and our place in the cosmos. One of the key areas in cosmology is understanding dark matter, which is thought to account for roughly 27% of the mass and energy in the universe. Unlike normal matter, dark matter neither emits, absorbs, nor reflects light, making it invisible and detectable only through its gravitational effects on visible matter. Understanding dark matter is crucial for explaining the formation and dynamics of galaxies. Recent observations have revealed more about dark matter's properties, but its exact nature remains elusive. Various candidates have been proposed, including weakly interacting massive particles, WIMPs, and axions, but no direct evidence of dark matter particles has been found yet. The search continues through a combination of ground-based experiments, astronomical observations, and simulations that model how dark matter affects the large-scale structure of the universe. Another crucial area of research is dark energy, the mysterious force driving the accelerated expansion of the universe. Dark energy makes up about 68% of the universe's total mass energy content. Its discovery was unexpected and has led to many theories, including the cosmological constant and dynamic fields like quintessence. Understanding dark energy is vital, as it will determine the ultimate fate of the universe. Scientists are examining how dark energy affects cosmic structures and attempting to comprehend whether it remains constant over time or evolves. Alongside dark matter and dark energy, the study of cosmic structure formation offers valuable insights into the universe's history. Observations of the cosmic web, a vast network of galaxies, clusters, and filaments, show how matter clumped together under the influence of gravity, leading to the complex structures we see today. Supercomputer simulations help scientists understand how these structures have been built over billions of years and continue to evolve. Astrobiology intersects with cosmology as researchers aim to understand the conditions that support life beyond Earth. The search for exoplanets, planets orbiting stars outside our solar system, has accelerated with thousands discovered in recent years. Some of these exoplanets are within their stars' habitable zones, where liquid water could exist. By studying these distant worlds, scientists hope to learn more about the potential for life elsewhere in the universe and what it might look like. Additionally, fundamental physics plays an essential role in cosmology. The search for a unified theory that combines general relativity and quantum mechanics continues to challenge physicists. Theories like string theory and loop quantum gravity aim to merge these two domains, offering potential explanations for phenomena such as black holes and the beginning of the universe. Advancements in technology are improving our capacity to observe and interpret cosmic phenomena. Space telescopes like the James Webb Space Telescope are revolutionizing our understanding of the universe by providing unprecedented detail on distant galaxies and cosmic events. With each new observation, we are gradually piecing together the puzzle of the universe's creation, evolution, and ultimate fate. In conclusion, the study of the universe is a rich blend of scientific exploration and philosophical inquiry. From the fundamental forces that shape cosmic structures to the search for extraterrestrial life, our quest for knowledge reflects humanity's deep curiosity about the cosmos. As we work to answer these profound questions, we not only gain new insights but also develop a deeper appreciation for the vastness and complexity of the universe. The relationship between observation and theory is central to cosmology, and innovations in technology, such as advanced detectors and machine learning algorithms, are enhancing our ability to analyze astronomical data. These tools enable researchers to sift through vast amounts of information, identifying patterns that could reveal new insights into cosmic phenomena. One important area of research is gravitational waves, ripples in spacetime caused by catastrophic events like colliding black holes or neutron stars. The detection of these waves has opened a new avenue for observing the universe. By studying gravitational waves, scientists gain insights into the nature of these extreme events and can test theories of gravity in ways that traditional techniques cannot. The concept of cosmic time is also intriguing. Unlike our everyday perception of time, which is linear and uniform, cosmic time is shaped by the expansion of the universe. This raises questions about the nature of time itself. Is it an absolute concept, or does it depend on the observer's position and motion? These philosophical questions parallel scientific exploration, highlighting the multifaceted nature of cosmological research. The formation of the first stars and galaxies, known as the cosmic dawn, is another critical area of focus. Understanding this epoch helps explain how the universe transitioned from a hot, dense state to the complex structures we see today. Observations of high redshift galaxies provide clues about the processes that occurred during this formative period, aiding scientists in constructing a timeline of cosmic evolution.